In the far future, scientist Sandy Gomez has devised a new transport system that she believes will transform travel across the universe. She has opened a series of wormholes capable of moving people through space at near-instantaneous velocity. For logistical reasons, she has set these up on planets that fall upon the same circumference. People will be able to travel from planets on the left side to the right by entering a wormhole in one direction, and from the planets on the right side to the left by entering a wormhole in the other direction. So far, nobody has been brave enough to test wormhole travel themselves, so Sandy volunteers to be the first. She crosses her fingers and jumps through the wormhole present inside her lab. Mind you, Sandy's lab is located on her home planet, denoted by letter D, and the wormhole she just jumped through is nothing but a space tunnel that connects planet D to planet C. The journey is successful, and Sandy gets the old-fashioned space train to planet B, home of the galaxy's prime commander, to tell her the good news in person. But when Sandy arrives at planet B and goes to put her makeup on, she notices something different about her reflection. There is a long gray streak in her hair. Oh no! Her assistant had warned her about this possibility. Going through the wormhole has changed her molecular structure and sped up her aging process. The only way to reverse it is to go through another wormhole of exactly the same length in the opposite direction. Otherwise, she may need a walking stick by the time the day is done. With no time to return to planet C, Sandy must figure out which wormhole from planet B is the same length as CD, the wormhole through which she originally traveled. Having worked on this project for some time, she knows that chords AB and CD are equidistant from the center of the circle on which all the planets lie. In other words, if OX and OY denote the perpendicular distances from chords AB and CD to the center of the circle, such that OX is equal to OY, can Sandy determine if chord AB is equal to CD? If so, prove how. Let's break down this problem by focusing on line segments AX and DY. We know that point X acts as the midpoint of chord AB, while point Y acts as the midpoint of chord CD. This is because the perpendicular drawn from the center of a circle to any of its chords bisects the chord. This implies that AB is twice of AX, while CD is twice of DY. In other words, if we can prove AX equal to DY, then twice of AX will be equal to twice of DY, and we'll know the chords AB and CD are of equal length. To do this, let's join point O at the center of the circle to points A and D on its circumference. This gives us two triangles, AOX and DOY. We know that angles OXA and OYD are both equal to 90 degrees. This is because OX is perpendicular to AB and OY is perpendicular to CD. Besides this, line segment OA is equal to OD. This is because radii of the same circle are equal to each other. Given that OX is already equal to OY, we can claim triangle AOX congruent to triangle DOY. This is because if the hypotenuse and side of one right-angled triangle are equal to the hypotenuse and the corresponding side of another right-angled triangle, then the two triangles are said to be congruent by the right-angle hypotenuse side criteria of congruence. Based on this, we can conclude that AX is equal to DY because corresponding parts of congruent triangles are also congruent to each other. In other words, twice of AX is equal to twice of DY. Or should we say chord AB is equal to chord CD? In general, this proves that chords that are equidistant from the center are also equal in length. Without wasting any more time, Sandy leaps into the wormhole, and her molecular structure is restored to its usual state. She'll have to go back to the drawing board with wormhole travel, but right now, she's just happy to get back her usual hair color.